So welcome back to Lean Together 2025. Our next speaker is Henrik Böving, who will tell us about automated bit-level reasoning in Lean 4.
Right. Thanks for the introduction. Thanks to the organizers. So I want to begin with a little motivation for why we might even need something like bit-level reasoning. So I brought a bit of C code. If you don't know C, it's not that important. So basically, what's happening here is we have a naive implementation of a random number generator. It's not a particularly good one, but it just does a multiplication and then a modulo with two very particular constants. And then if you look around on the internet, you will find alternative implementations of the modulo part of this RNG that look like this mess. So there's like some AND happening and some bit shifts over here, and suddenly there's additions and so on. And we claim that, or the people on the internet claim that these two are the same, but in fact, the second one is quite a lot faster than the first one when you're benchmarking it. So of course, you might want to verify this claim. And if we want to do that in Lean, the first thing we have to do is translate it to Lean, of course. And for that, you already have our bit vector primitive. So a bit vector is just an n-bit integer. So in this case, 32-bit integers. And it's a bit more verbose, mostly because we don't have the nice cast that C has, because we are talking about n-bit integers and not just Q and 64 and so on. But you should still be able to make out the structure from the previous slides. And then we can state the correctness theorem, which just claims if we have some state for the RNG, and the state is within these bounds, and in fact, these bounds are important, otherwise the theorem doesn't hold, then the naive and the optimal implementation always agree. And if you want to prove that, we can, of course, try to unfold naive and opt, but then it's quite unclear what to do now, because, I mean, there's no apparent connection, probably to most listeners, between the modulo and whatever is happening here. However, in principle, state is a finite problem domain, right? So we should be able to just do a very large case distinction on all of the bits in state, and then show essentially by brute force that this ends up working out. And that's exactly what BBDecide is doing, though it has, of course, a very intelligent version of brute force. And the way it works is heavily inspired by BitWutzler SMT solver, which is currently the top SMT solver for these kinds of problems. And it basically goes in 4 steps. We initiate a normal proof by contradiction. Then we do some pre-processing that we're going to take a look at in a moment. And then we take the conjunction of all of the bit vector hypotheses that are left and turn them into a Boolean circuit, which is usually referred to as bit blasting. And now, if we can somehow show that the circuit never outputs true, which is to say it always outputs false, then we have an hypothesis that says false is equal to true, so we have a contradiction. And to give a little illustration of how all of this pipeline works, I cherry-picked a proof where BBDecide was used at an AWS project. So we have just 3 variables here, 64-bit, and then a hypothesis that n is less than big scary constant minus k, and k is greater than 0. And we want to prove a plus k is not equal to a. Well, that's quite obvious. And also n is less than, and this is the bitwise negation of k, which is not at all obvious. So we start with our proof by contradiction, right? That should be familiar to everyone. And then we begin with the pre-processing pipeline. And the first step of that pipeline is applying a lot of custom pre-processing rules that we basically took from BitWutzler. BitWutzler has about 200 of these rules, but of course, if we apply them in Lean, we need to verify them. So we haven't really gotten around to verifying all 200 rules. So it's currently about 60 to 70 rules. But as you can see, the ones we already have are doing like a lot of work here. So for one, they are turning everything into just stuff about booleans and bit vectors for simplicity. And then somehow they also made the big scary constant go away, and suddenly there is bitwise negation of k over here. And they also turned k is greater than 0 to k is not equal to 0, because that's easier to work with later. And the next step is called end flattening, where we basically look through all of the hypotheses that we've collected so far. Do they consist of a conjunction? So in the case of H1, there's a conjunction, so we can split it into H1 and H3. In H2, there's also a conjunction, but it's currently hidden underneath this negation here, so we can't split that. And the reason that we are doing the splitting is mostly as a preparation for the next step, which is embedded constraint substitution. And that's basically equivalent to sim star at star. So in this case, we can substitute H1 in H2, right? Otherwise, no substitutions available, unfortunately. And then we are left with this end true here. And of course, there's now more opportunity for rewriting. So we basically run this pipeline in a fixed point loop until we eventually converge. And then we collect all of the hypotheses into one big conjunction. So here we can remove the end true, and then there's a double negation here that we can also remove. And then we are left with this part. And now we need to translate this into the previously mentioned circuit. So what we do for that is first a more technical step, which is called proof by reflection, where basically you define a data type that represents the kind of expressions that you want to work with. So in our case, we have like bit vector expressions that have variables and constants, and you can add them and all the other cool stuff that we have. And then you define some semantics of these expressions with respect to some variable assignment. And the cool thing is that you can now write a meta program that takes like a lean level BitVec expr, like x+1, and it produces a BV expr over here that is then definitionally equal to the original BitVec expr. So what we can do is basically run a program that reflects this into a bool expr that then contains BV exprs. And then we can do proofs about these BV exprs. And in the end, just say, okay, we know something holds about these BV exprs, and they are def EQ to our lean exprs. So that also holds about our original hypotheses. Right. So then we need to prove something. So now we go to the circuit translation. And for that, we, of course, need a notion of circuits. And Bitwurzler uses so-called AND inverter graphs for this. And an AND inverter graph is just a kind of circuit with three kinds of things. So we have input nodes here, 0 and 1, then AND gates 2 and 3, and then these AND gates are connected to each other. And here, depending on whether the color is red or blue, the input to that particular AND gate is either inverted or not inverted. And the way we represent this in Lean is through this Deckel data type, where we can have either constant nodes, of course, so constantly true or false nodes, input nodes, or gates. And one particular thing here is that the left and right side of gate is not a declaration, but a natural number. And that's because we want to have sharing in our circuit. So if you look here, 3 and 2 both share this input node 0 here. So the way this is implemented is in the AIG itself, we have an array of declarations, and then L and R are just indexes into this array. So over here is basically the array representation of the circuit below. And the last gate here has as a left input the 0th index, which is the atom 0, and then is its other input the second index, which is this gate, and so on. And of course, when you're building the circuit, like when you're adding new nodes and so on, while you do the translation, you need to know, like, am I right now building a node that already exists in the circuit to then reuse it, of course. And for that, we have this cache. which is a wrapper around the formally verified hash map that we recently added into the standard library. And it's just a hash map that goes from declarations to indexes in the array. So when you're adding a new node, you first build the node and then you just ask the cache, hey, does this exist already? If it exists, you just use that index. And if it doesn't exist, you add that node to this array and then you continue on. And then lastly, there's an invariant that these circuits form directed acyclic graphs because we are not interested in circuits with cycles here. And of course, this structure is mostly performant because of the in-place updates that we have in Lean, right? So the array here and the hash map underneath the cache will both be updated just like in an imperative programming language. So this is a very fast data structure to build circuits with. And what we need to do to use this is first write lots of translators from BVexpr to AIG for all of the bit vector operations that we support. We need to write a function that produces a circuit that computes this bit vector operation. And then we need to build a lot of AIG theory to show that the circuit we are building is doing the same thing as the BitVec that's behind this BVexpr that we are working with. And the BitVec theory half of this was done by Siddharth Bhatt. Thanks a lot for that. Right. So now we have our circuit. And the next thing is we need to show the circuit can never output true. And for that, we are going to use a SAT solver. And just a brief explanation, if you don't know SAT solvers, basically we give them a Boolean formula, and the solver will try to find a variable assignment that makes this formula true, and we say it's satisfiable, hence the name. And the important part for us is if it cannot find such an assignment, it's actually going to produce a so-called unsat certificate. And these certificates are, in essence, step-by-step proofs or proof sketches to show that the formula we gave it is equivalent to false. And these proofs can be very long, like we're talking about potentially hundreds of thousands of proof steps here. But they are also very easy to reproduce, so to speak, or to turn into a real formal proof. So what we do is we take the circuit, we give it to a SAT solver, in our case to Katikal, which is currently one of the top solvers. And if it returns SAT, so a variable assignment, we can actually recover counterexample, because then evidently there does exist some variable assignment for which our hypothesis is not equal to false. So we have a counterexample that we can present to the user. And if it returns unsat, we get the certificate, and then we run a verified certificate checker that just checks, is the SAT solver doing a correct proof here? And that checker that we're using was written by Josh Kloon during an AWS internship. And now there's one additional issue because we are in Lean. So far, I've been talking a lot about executing programs at lightning speed because of our optimizations and whatnot. But, and of course, the SAT solver, calling to external programs and so on. But the Lean kernel, of course, doesn't believe in SAT solvers or executing programs just like that. That's not part of the trusted code base of the Lean kernel. So we now need to do some tricks to convince the Lean kernel of the proof idea that we have here. And for that, we need to write some basic theory. So we need to write a correctness theorem for the checker, which just claims we have some CNF, and CNF is just the input format for a SAT solver. So this is basically our circuit. And then a proof certificate. And if the checker says, OK, then that CNF is unsat. And then we can write this function here, which takes our bit vector expression that we previously recovered from the proof state and the LRAT certificate. And then it performs bit blasting on that bit vector expression. It turns it into a CNF, and then finally runs the certificate checker on that. And then using this theorem and all of the theory about circuits and so on that we built previously, we can prove that if this verify function claims or if this verify function outputs true, this BVexpr is unsatisfiable. So the only thing left is basically, how do we convince Lean that this very computationally expensive function outputs true? And for that, we have a particular axiom that you can opt into, which is the off-reduce bool axiom. And this basically says, hey, Lean, take this expression here, try to execute it, and if it returns true, then just believe that, right? So for this very particular moment here, for this particular sub-expression, we are telling Lean, run this thing with native code, just trust the compiler, trust the computer, everything, and then continue on with your normal reduced code base. And like that, we can then import our proof certificate into Lean, basically. So to summarize, what we're doing with BVDecide is we do a proof by contradiction, then all of the fancy pre-processing, this proof by reflection to get our BVexpr out, and we bit blast it, we give it to the SAT solver and either get a certificate or a counterexample. And then finally, we use off-reduce bool and our answered certificate to show that the expression is equal to false and thus arrive at a contradiction. And what we can do now is basically just import BVDecide, put BVDecide here, and it's going to finish, right? And BVDecide knows all of the built-in BitVec stuff, so this is just going to close the proof in a couple of seconds. And that's pretty great, of course. But now there arises a natural question: is a couple of seconds fast? Like, how fast can we expect such a tool to be? And for that, we did some performance evaluation. And to evaluate our performance, we of course need some tools to compare against. The most obvious tool to compare against is of course Bitwurzler, because BVDecide is implemented like Bitwurzler, but Bitwurzler for one has a lot more tricks, and secondly, doesn't need to verify all of these certificates, doesn't need to do any type checking and so on. So it's almost certainly an upper bound of what we can expect to achieve performance-wise. And then we can also compare against other ITPs. Holite also has a Cadical-based bit blaster. Coq has two tools that we'll look into. And lastly, Isabelle, unfortunately, as far as I know, doesn't have anything that goes in this direction. So we can't compare against Isabelle. Right. And the first benchmark is BVDecide against Bitwurzler on a data set generated by the Lean MLAR project. And this data set contains rewrites from the LVM inst combine pass. So this is real-world compiler rewrites that all of the C compilers, Rust compilers, Swift and so on apply on a day-to-day basis. And we are giving them to Lean to try, and Bitwurzler, of course, to try and verify them here. And the way to read this graph is we have on the x-axis a logarithmic timescale in milliseconds, and then here amount of problems solved. And if you go, for example, to approximately 2,500 over here, then this says the first 2,500 fastest problems are cumulatively solved in 10 to the 5 milliseconds. Right. And as we can see, apart from like a few outliers towards the end, Bitwurzler is performing basically just a small bit faster than BVDecide, which is a pretty good result because, as previously mentioned, it's our upper bound. Next comparison is against Holite. Unfortunately, of course, there doesn't really exist a great set of problems that are shared between Holite and Lean, like just on a syntactic level. For the Bitwurzler part, we could just export the problem to the standardized SMTlib format, but I don't know much about Holite. So what I did is take their example file for bit blasting and manually translate it to Lean. So we only have like 20 problems here, so this is not really representative. But of course, we can certainly see a trend here. That being said, of course, if there's some Holite people that are watching this that want to evaluate the performance further, feel free to reach out. Yeah. And then going over to the COG tools, we have first SMT-COG, which has a slightly different approach to BVDecide. SMT-COG asks another SMT solver called CVC4 for a proof certificate directly. So they don't do any translation into like circuits and so on. They just give the problem to CVC4, and then CVC4 gives some kind of not so detailed proof sketch that they then try to replay into COG. And this works great for some other SMT theories, like, for example, linear integer arithmetic and so on. But as we can see in this issue, when you're doing bit vectors, it's unfortunately rather slow. So this user here has two 64-bit variables, x and y, and both of them are equal to 0. And they want to prove that x is equal to y. And that's taking about a minute with SMT-COG. But CVC4 doesn't take any time at all. So almost all of this time is spent replaying the proof into COG. And for that reason, I didn't really do a performance comparison because evidently SMT-COG isn't optimized for this use case yet. Right. The second tool is COG QFBV, which is also a slightly different approach. COG QFBV is an implementation of a normal SMT solver in COG. So they are not integrated into COG as a tactic. They don't do any of this proof by reflection stuff, no overhead of the type checking and so on. They have a program written in COG, and then they extract it to a kernel and run it as a normal binary. So we have an inherent handicap compared to them. One additional thing, they use a different certificate checker called Jira check, which is written in Isabelle. So even if they wanted to integrate it into COG, they would also need to rewrite this certificate checker. So this isn't really a trivial effort to make a tactic out of for COG. But anyway, despite being handicapped, we can, of course, compare against COG QFBV. And the standard way to benchmark SMT solvers is the SMT-lib dataset. And this dataset, as we can see, contains tons of problems. Overall, it's about 45,000. And they are grouped into two parts. So for one, we have the sub-problems. So in our terms, the ones that we can expect to find counterexamples for. And then the unsub problems, so the ones that we can expect to find a proof for. And then we can benchmark BitWurzler, BVDecide, and COG QFBV on all of these problems. BVDecide here is benchmarked by basically writing an adapter that consumes the SMT problem format and turns it into a lean proof, and then just runs normal BVDecide. And this data was collected by Abdal Mohammed on a cluster in Stanford. And as we can see here, we solve about 65% of the problems overall. On SAT, like on the SAT half, we get very close to what BitWurzler can do. Of course, BitWurzler is still a lot faster, but towards the end of the time limit, we are all very close to each other. But interestingly, on the unsub part, there's quite a large gap between BitWurzler and both COG QFBV and BVDecide. And there is a couple of reasons for that. For one, as I explained previously, they don't need to do any of the certificate checking and so on. But also, BitWurzler invested a ton of time into being good at this data set, right? They have all of the rewrites, optimizations, etc. So it is to be expected that they perform very well here. And additionally, SMT-lib contains a lot of problems that are very large. So we can expect to see problems that contain like large C files just translated one-to-one into BitVec and then thrown at the SMT solver in hopes of finding a proof. And of course, as the problems grow very large, the proof certificates grow very large. So both CoqQFPV and BVDecide need to do like a lot more inherent work compared to BitWutzler. And as mentioned previously, we just have a natural handicap compared to CoqQFPV because we do a bit more work. Right. And that already gets us to the future work section. The first thing is, of course, we can now do optimizations based on our observations in the SMTlib dataset. We saw that 4,000 problems time out while we are in the kernel type checking, the reflection and pre-processing. So exactly the stuff that we don't do in CoqQFPV. So we can try to optimize the kernel terms and so on here. 7,000 problems time out while we run a SIMP already. So we can try to make SIMP work better on large proof terms and so on. And then there's 4,000 other problems that are stuck in other parts of the pipeline that we can, of course, also work on. And in terms of features, I'm going to be working on 3 things this quarter. So for one, we want to support our uint and signed int fixed width types as well, which is like, quite an obvious reduction, right? We have like 8-bit unsigned integers. That's obviously a bit vector. Then we want to support structures of all of our supported types automatically. And lastly, also enumeration types. So when you have like inductive A or B or C or D, that's an enumeration like in C or Java that you can, of course, also do this kind of, this is a finite type, let's do case distinction analysis on. So in conclusion, what is BVDecide? Well, it's a tactic that we can use to solve all fixed width BitVec problems in Lean, assuming that it doesn't time out, of course. And on our ITP size problem set from Lean MLAR, we saw it performs very close to BitWutzler, so very close to as good as we can probably get. And on SMTlib, we are already producing acceptable results, and we know how to optimize further on that. So we expect to see the percentage grow in the future. And that's it.